History of Vector Analysis, Episode 5, Complex Numbers and Geometry. You are here. Hey, it's old Doc Goler. Welcome back. Previously, we discussed how Cardano first considered some of the arithmetic properties of the square roots of negative numbers back in 1545. Progress from there was slow, but Leonard Euler essentially completed the work on the algebra of what we today call complex numbers in the late 1700s. Not discussed in this series is the concept of analytic geometry or coordinate geometry. This type of geometry's invention/discovery is mostly accurately attributed to René Descartes' publication in 1637, although it didn't become widely known until the 1660s, some 20 years later. It involves a coordinate system. A coordinate system, as you know, is composed of number lines along perpendicular axes with negative numbers and an origin. Today, the concept of the number line is introduced in the second grade. Okay, but it took mathematicians a surprisingly long time to develop the concept, in large part because of their reluctance to accept the legitimacy of negative numbers. Descartes is credited with laying down number lines on both the x and the y axes and then expressing geometric curves in terms of the resulting coordinates. Regarding negative numbers, I will state that Descartes himself worked mostly in the first quadrant where all of the x and the y values are positive. I will just say that it did occur to various people in the 18th century that a coordinate system akin to the xy plane could be applied to Euler's new z equals a plus ib type complex numbers, but none made much progress until a guy named Casper Wessel came along. This is Casper Wessel. He was a Danish-Norwegian cartographer or mapmaker and is credited as the first person to describe our current geometrical interpretation of complex numbers. Wessel was just a guy, a mapmaker who used some math and was not a formal mathematician. He only wrote one paper of significance, which was presented to the Royal Danish Academy of Sciences and Letters in 1797 and was published in 1799. Here it is. This paper, written with the help of an insider, the president of the science section of the Royal Danish Academy, is entitled On the Analytic Representation of Direction, an Attempt. Unfortunately, it was written in Danish and not widely disseminated. In fact, Wessel's paper quickly vanished without a trace. The work was independently redeveloped by the legendary Carl Friedrich Gauss in 1831 after Wessel had died. Gauss, being a big name in math, brought legitimacy to some of the crazy ideas that were presented as well. So 1831 is really the year that Wessel's ideas became known to the mathematical community, and that was because of Gauss. But whatever, spread the wealth. I note that Gauss also coined the term complex numbers for Euler's z equals a plus ib things in this 1831 paper. What exactly did Wessel do? Wessel explicitly drew what we today call the complex plane as an analogy to the Cartesian plane that had been around for over a century by this point. Instead of x and y axes, it had a real and imaginary axis, and complex numbers could be expressed as a point on this quasi-geometric plane. Now, Wessel was not really the first to do this. Others had tried it, although they all ran into some interpretation problems that we tend to gloss over today. Specifically, if the x-axis corresponds to the real and the y-axis corresponds to the imaginary, what does the z-axis correspond to? Oh, and aren't there three real axes, not just one? There's a fairly significant suspension of disbelief that is required to not instantly gag on the concept of the complex plane. But that's not all that Wessel did. Wessel's paper contained two original lines of thought. The first, shown here, involves the addition of not just real and imaginary numbers separately, but adding what he called sloped numbers, recall the term complex numbers wouldn't be coined for another 30 years, on the real imaginary plane. This is what we think of today as the parallelogram method of vector addition. He got internally consistent results. A plus B gives the same result as B plus A in a visual/geometric way. This, believe it or not, is the beginning of vector analysis. Now, this seems almost trivial today, but it was revolutionary at the time. Michael J. Crow, whose book is the primary reference for this series, wrote, The idea of the parallelogram of velocities may be found in various ancient Greek authors, and the concept of a parallelogram of forces was not uncommon in the 16th and 17th centuries. But the idea of adding the lines need not be introduced, nor was it, to my knowledge, says Crow, ever introduced before the creation of vectors. Wessel's second original line of thought ran like this. If you really want to use complex numbers as mathematical objects, then simply being able to add and subtract them is not enough. You need to define multiplication and later division and exponentiation. Now, as I showed in the last episode, Euler had already done all of this algebraically. He did it with the now standard approach of cross multiplication shown here. What Wessel is credited as being the first, or as one of the first to recognize, was an interesting pattern in the real imaginary multiplication table shown here. Part of the reason that others hadn't noticed this was continued reluctance to consider negative numbers, or in this case, negative coordinates. As noted, most of the examples done to this point involved what we today call the first quadrant, where the x and y coordinates are both positive. Wessel considered not only negative real numbers, he considered negative imaginary numbers on this modified Cartesian axis and in his multiplication table. Wessel noted something interesting about the I row of the matrix, with its terms rearranged slightly here. If the 4 points of the geometric grid with magnitudes of 1, that is to say 1, minus 1, plus I, and minus I, were multiplied by I, then the product was always shifted by 1 to the left. See, here you get I and I, minus 1 and minus 1, minus I and minus I, plus 1 and plus 1. Okay? He saw that this had a geometrical interpretation, a rotation of 90 degrees in the complex plane. This was something new, perhaps even a holy grail, a return to the visual clarity of geometry, albeit via the semi-incomprehensible complex plane. Okay, does this hold out for other multiplication numbers? Well, if you multiply by I twice, it's the same thing as multiplying by minus 1, and plus I goes to minus I, and plus 1 goes to minus 1. All right, looks promising. Does it generalize? If this mathematical interpretation were to be general, multiplying one complex number by another would correspond to a rotation in the complex plane along with some sort of scaling or stretching. His simple but clever mathematical approach was to convert these complex numbers into polar coordinates. Hopefully you can do this transformation between Cartesian and polar coordinates in your sleep. If you can't, okay, you really need to learn this, okay, fast. But continuing, consider coordinates r and theta instead of x and y. In two-dimensional polar coordinates, r is a length, a magnitude, and theta corresponds to an orientation, a direction. You can see where this is going. Okay? Complex numbers expressed as a magnitude and a direction. Vectors. There is an important subtlety here, though. Nothing up my sleeve. I have tacitly converted a point, 0 dimensions, into a geometrical line of 1 dimension by connecting that point to the origin. Okay? I have magically transformed a point into a line. Standard practice, folks. Nothing to see here. Move along. I do intend to discuss this in more detail if I ever do that series on the history of analytic geometry, which is where this came from. Let us consider 3 points, A, B, and C, in the complex plane, drawn and defined in both Cartesian and polar coordinates. We are going to multiply the complex number A by B, as before, only this time we're going to do it in trigonometric form. Thanks to Euler and those guys, we know going in that the product will be another complex number, call it C. The question is, can we get the same number C by starting at A and then rotating it geometrically by something associated with the complex number B? Let's do the math both ways. First, we'll do it algebraically by cross-multiplying in the standard way. We get this expression, note the I squared term, which we can rewrite as minus 1. By the way, I reiterate all these charts are available on the website if you want to go through them more slowly. Okay, next we'll group the 4 terms into reals and imaginaries, and here's the result, A times B. Now let's consider C. By the rules of Cartesian polar conversion, c has to be expressible as this: the magnitude of c times a cosine of an angle plus I times the sine of an angle c. So here is a times b, and here is c, written in polar coordinates. Algebraically, for these two statements to be equal, we need three things. First, the magnitude of a times the magnitude of b must be equal to the magnitude of c. Second, the real part of the AB expression must be equal to the real part of the C expression. And third, the imaginary part of the AB expression must be equal to the imaginary part of the C expression. But that's not all. For Wessel's rotation interpretation to hold generally, we have a geometric requirement that must be met as well. Angle A plus angle B must equal angle C. Now, this is pretty weird when you think about it. Theta C must be equal to the sum, not the product, but the sum of theta A and theta B. Today, such requirement would instantly call to mind logarithms and exponents which behave this way. But still, weird. Well, this expression is pretty messy. Is there any way to simplify this? Why, yes there is, if we remember our sine and cosine addition and subtraction formulas from high school. For the real part of a times b, this term over here, we can see that this lines up pretty quickly with this one right here. So we can express this longer expression with this shorter one. What about the other side? Well, we don't have cosine a sine b in here anywhere, but we do have cosine a sine b here twice. And in fact, this one here has got sine a cosine b right there. So because these two terms commute, we can identify this as it. And the result is AB times cosine of this plus sine of this. Okay, but wait. In both of these cases, the resulting angle is the same, A plus B. Okay, are we on to something here? Yes, we are. If the magnitude of the point C can be expressed as the product of the magnitudes of A and B, and if the angles A plus B equal angle C, then we get the same expression for C this way that we did by cross multiplication technique. A times B equals C for arbitrary A and B. Woo-hoo! Is this for real? Let's do a specific example. Here's the image again. Now let's state explicitly the coordinates for A and B. Here we go. I have picked A to have a 45-degree angle with respect to the real axis, so each projection has got a magnitude of 1. I have picked B to have a 60-degree angle, and the imaginary coordinate is equal to 3/4. These then are the Cartesian coordinates. If we multiply this out in the standard fashion, we get this, which reduces to this, and then this to three significant figures. Now, let's do this again in Wessel's vernacular. First, we express the points A and B in polar coordinates thusly. Now we calculate C equals A times B by multiplying the magnitudes and adding the angles. See, multiplying the magnitudes and then adding the angles. Here's the cosine part and the I sine part. All right. This works out to be this, which in turn goes off and reduces to this. They're the same. Okay? So multiplication of complex numbers algebraically can be interpreted geometrically as rotation in the complex plane. If you aren't at least a little bit impressed that all this works out, then I guess all I have to say is congratulations, you are probably not a troubled physics major. Normally, this is where I would end the episode, but I want to add a couple of thoughts that ride on this discussion, which I don't think would fare well as a standalone episode, so I hope you'll forgive me for keeping you for a few more minutes. One of the first things Wessel's work does is allow us to come up with a geometric interpretation of Euler's formula. It turns out to be a special case of the coordinate transform with the magnitude of the complex number being set to unity. This also illustrates the relationship of trig functions to exponential functions when dealing with complex numbers. The key observation to make is that in complex multiplication, while you multiply the magnitudes, you add the angles. There is another place in mathematics where multiplication translates into addition, and that is exponents and their inverse operation, logarithms. This is another interesting property of complex numbers that doesn't work with real numbers. It's almost as if complex numbers are better or more true than regular numbers. Almost. Okay, that's all I'll say about that. Next, a few words about the idea of I, the square root of -1, as the 90-degree rotation operator. This is a legitimate interpretation. However, there are a lot of statements out there claiming that this proves that complex numbers have a geometrical interpretation, something that Descartes and others failed to find. Okay, my view is, well, sorta. Once you assume the complex plane, complex numbers can be interpreted as rotating and stretching one number into another. But about that assumption, what is the geometric interpretation of the complex plane itself? I personally don't think Descartes would be impressed with this idea, for whatever that's worth. Complex numbers as the first vectorial system. My guy Crow writes, though the term vector analysis is now used primarily in reference to systems of mathematics that may be applied in three-dimensional space, it should not be forgotten that the complex number system may legitimately be considered as a vectorial system. Okay? It's got magnitude and direction, even though it seems to be hard limited to 2 dimensions. It is from this point that William Rowan Hamilton will take the next step, an intermediate one between the complex numbers and the vectorial system that we know today. Right up front, however, spoiler alert, I need to point out that while there is a great deal of overlap between the rules of complex number addition and vector addition, they diverge radically when it comes to multiplication. First, the rules for determining the magnitude of C equals A times B are different. In complex numbers, the magnitude is A times B. In the vector dot product, the magnitude is AB cosine theta, and the vector cross product, the magnitude is AB sine theta. The rules for determining the direction of the product are even more different. We have just shown the rather brilliant discovery that in complex numbers, the direction of the product angle theta C is theta A plus theta B. In the vector dot product, the direction is not defined. You get a scalar, which has a magnitude but no direction at all. In the cross product, you don't add theta A to theta B. In fact, the direction of A cross B is independent of the angles theta A and theta B because it's perpendicular to both. So there are important differences as well as similarities. Next, just a couple of words about how the metaphysics of mathematics was altered by the introduction of complex analysis, or the way it was referred to at the time, double algebra. The introduction and acceptance of double algebra after 1831, when Gauss, he at the big name, reintroduced it, was earth-shaking to the mathematical community. Okay, well, it would have been earth-shaking had the not even more disruptive non-Euclidean geometries started to appear at about the same time. These are interesting times. Okay, the 250 years or so between Cardano's Ars Magna and about the year 1800 is a rough measure of how long it took to cross the metaphorical desert of the imaginaries. By 1800, the far side had been reached. There was an end to the wasteland. Complex numbers not only had well-behaved algebraic properties and even a quasi-geometrical interpretation, but more and more useful applications were being found for them, albeit almost entirely within the mathematical community itself at the time. As the Industrial Revolution approached, and with it the dawn of our modern understanding of electricity and magnetism, complex numbers were about to become an essential tool for engineers and physicists alike. However, there was this weird side branch that shot off in a significantly different direction as well, one that led to vector analysis. I will begin that part of the tale in the beginning of the next episode when I introduce William Rowan Hamilton. Okay, that's it for this episode. Thanks for hanging with me. See you next time.